Welcome back to this video about friction and the origin of friction. In this part we will discuss the adhesive component of friction. And what is that then? Well, this is an illustration of a kind of schematic illustration of two surfaces. So the green ones is surface 1, the atoms of surface 1, and the blue ones are the atoms of surface 2. And of course, there is always some kind of force field in between atoms like this. Also, inside the material itself, then we talk about cohesive forces, and we talk about adhesive forces when it's in between dissimilar materials like this. The adhesive forces are very short range, some like nanometers or less, and so if surfaces are far away from each other, the adhesive force is very small. And of course, the force itself in between two atoms is very small, but there are so many atoms, and the total amount of contacts between atoms could create very high friction forces in some cases. You can also say about adhesion that the more dissimilar the two materials are, the lower the adhesion is. That is something called metallurgical compatibility or mutual solubility. We will come back to that later. I can also say that if you create an oxide layer on the surface, well, then you create a metal oxide, for example, on the surface here. That also makes the materials different from the other surface, and that also then reduces the adhesive friction. I will bring up something also called the elastic recovery, just to illustrate that that you may have friction even if you don't have any normal load at all. So let's continue on that. Some thinking about adhesive friction then is that the adhesive friction coefficient is the adhesive friction force divided by the normal force. Well, what is that then? The adhesive friction is the shear strength of the interface of the surface multiplied by the real air contact, and the normal force is approximately the hardness multiplied by the real air contact. That means that the adhesive friction component is the shear strength divided by the hardness. For many metals, the hardness is proportional to the yield strength. Why? So it's about 3 times the yield strength, and so is also the shear strength of the surface. It's about half the yield strength. So putting that into the first equation, it means that the adhesive friction coefficient is around 1/6, and that is also what you find if you make an experiment of clean metals in air. You measure the friction force to 0.2 approximately. So that's something to have in mind. Coming back to this about metallurgical compatibility then. That has been a research area during the 1900s, and one famous tribologist, Rabinovich, he saw that there was a relationship between static friction or friction and metallurgical compatibility, even if it was discussed that other people didn't see that much. But especially when you increase the temperature, when you approach scuffing, that is when the surfaces are so warm that or hot that they start melting, and then you have a very good high adhesive force, and then you can see the difference. And let's take a look here on iron, which is or steel is a very important material, of course. You can see that iron is compatible to some materials like zinc, aluminium, gold, copper. They have a a good compatibility, while it hasn't a good compatibility to lead, indium, and silver. And this you can make use of that in many ways. For example, lead has been used. It's not nowadays. It's not allowed to use lead very much, but lead has been used as a friction material because it's poor compatibility with iron. We'll take a look on an example of aluminium instead. Aluminium is an important material, and it's growing. For example, in cars, the metal sheets of the car, you start using aluminium instead. So then you need to form the aluminium, and so forming with a steel tool is very common. And since it has a high solubility with iron, it's softer than iron, it can create big problems if the oxide layer breaks. Remember now that aluminium has a strong oxide layer, so you have a layer that separates the aluminium atoms from the iron atoms on the steel. But if we break the oxide, then the aluminium wants to stick to the steel, and then more and more aluminium is transferred to the steel surface, and eventually you have a contact in between aluminium and aluminium, and that aluminium contact is creating a high friction and could even create a seizure. But as long as there is no transfer film, as long as the oxide is remaining there, you maintain a friction which is relatively low, say 0.2, or friction coefficient that is relatively low, say 0.2. So this is adhesive friction problem, you can say. And of course here it's important to keep the harder surface as smooth as possible to avoid the plastic deformation of the smoother surface, which scratches the oxide film and makes the adhesive friction possible. So here you can also see a relationship between plowing or abrasive type of friction and adhesive type of friction. Before discussing more how to avoid adhesive friction, I will also want to mention elastic recovery. That is a little bit a funny effect. If you have an elastic contact, a purely elastic contact, the real area of contact is 0 before applying any load. If you apply the load, the real area of contact is bigger than 0, of course. If you have an elastic plastic contact instead, then after loading and unloading, you still have some contact or a contact area here because of the dent created by the indenter here. So the real area of contact isn't 0, and due to the adhesive forces, you have a interaction between the surfaces that causes a friction. I think you have played around with this gauge type of plates, putting them together, and then they maintain stuck even if you reduce the load. Okay, coming back then to the problem of how to reduce the adhesive part of the friction. Well, as we discussed, even if it was a little bit discussed before by people, it's always good to have similar materials. We know that's the reason why brass is normally often used in contact with steel in some cases. You can introduce something in between to avoid that the short range forces can play an important role here. That is by creating some layer, carburizing, nitriding, or oxidizing the surfaces. You can put a lubricant there, or some molecules in the lubricant. You can put a coating there made of a material that is dissimilar than the other materials. So in general, you can put something there with a thin metal layer with a low shear strength also. That you remember the equation I showed, the tau over h. Of course, if you can do that, then you also get this effect. That could be a very soft metal, of course, a very thin layer of that soft metal. Could be silver, could be indium. You could also maintain a high hardness of both surfaces, because then you keep the real area contact small, and there is always only a small spots where the adhesive forces can play a role. And in this case, you should avoid making the surfaces too smooth. So just of the same reason as the previous bullet here, you want to keep the real area contact small enough. Don't make it too small, then you get a lot of plastic deformation. But if you keep it on a reasonable level, then you avoid big patches of adhesive forces. So you can think about this when you see these three cases. You can stop the video and think about the solution to this question. Which is the best combination from a low friction point of view? Should you take you have two surfaces, one soft, one hard. You make one of them rough and one of them smooth. Should you make the soft surface smooth and the rough surface hard? Or should you do it the other way around? Or you take the two soft smooth surfaces, one soft and one hard? Or should you take a rough soft surface in contact with a smooth hard surface? Which one of those three cases will give the lowest friction? Think about that for a few minutes. All right, the solution is, of course, that you should take the rough soft and put that in contact with the smooth hard. And why? Well, first of all, the hard one should be as smooth as possible, then it can't penetrate into the rough one, then you don't get any abrasive type of wear or plowing type of wear or friction. And because you make the soft one rough, you also reduce the real area of contact, so you only have a few contact spots here where you can have adhesive friction. So by combining the surfaces in this way, you reduce the dry friction. So that's something, this is a kind of tribological rule, I would say. A few words about some other friction phenomena, starting with static friction. If you have two surfaces, they are in contact with only a tiny spots here and there in the asperity contacts. If you leave them there for a longer time, they actually, the contact spot grows continuously due to creep, and maybe there are also contaminants or corrosion taking place that you make the contact spot to grow. So the contact spot grows more and more, so that means that the adhesive friction will increase with time. Now when I say time, I talk about minutes, hours, years. So the adhesive friction will increase with time. So that's something to think about. You may even happen to have two surfaces that stick together very, very much after leaving them for a long time. So leaving two very smooth surfaces together is a very bad idea, for example. Another friction-related phenomena I want to mention is the stick slip. Stick slip occurs if the static friction is higher than the dynamic friction, or if you have a negative mu versus speed curve, slope of the curve, of the mu slip curve. What is happening then? To illustrate that is we have a box here, and you pull the box with a kind of elastic wire, for example. And if when you increase the force here, the guy is pulling here, you increase the force. The spring is prolonged, and then eventually the force is high enough to overcome the static friction force. But when you do that, the friction goes down to the dynamic friction level, and the box catches up the guy pulling the box, and the force is reduced, and it may be reduced so much that it becomes smaller than the dynamic friction force, and the box sticks. And then you have to increase the force again to overcome the static friction force, and it starts sliding, and then it sticks again. So it sticks and slips and sticks and slips. The same thing may happen if you have a moving system all the time, but if you have this negative mu speed curve slope, then the same thing happens when you increase the speed. It will catch up the guy pulling here if you use the same model, and the friction will go up, and you need, or go down, and you release some of the stresses in the spring, and it will slow down again, and then it will increase again in speed, and it will decrease, increase, and decrease. It's not a stick slip, it's more called a shudder in that case. And it happens in automotive clutches, for example. You can hear that as a noise in a clutch. You can also in general, stick slip creates vibrations that gives you a noise. But it's actually also the same phenomena that excites the string of the violin and creates a beautiful noise of the violin. How to prevent stick slip then? Well, you can introduce damping of the, you can, instead of having a perfectly elastic spring here, you have some damping there too. You may have very high stiffness of the spring, but most important, you should try to keep the static friction the same as a dynamic friction, and you should avoid the negative slope of the mu velocity curve. That is to avoid both stick slip and shudder then. So let me conclude. Friction is a pretty complex phenomena, and it's even if I have mentioned now a number of effects or causing the friction, it's still they are interacting with each other, and they change in nature. If you increase load, they change speed because you break the oxide layers. You may change the conditions by just sliding the surfaces in contact. So it's very difficult to predict it, and there are no models. So normally we do have to use some kind of friction coefficients in order to predict the friction, or predict the influence of friction in a mechanical system. So that's it about friction and or abrasive and adhesive friction. I'd recommend you also to watch the videos about rolling friction, for example. Thank you very much.